modern kaleidoscope of real symmetry. So it's a great pleasure to introduce Seidel from MIT, who's going to tell us about Fano manifolds and formal groups.
Okay, thank you very much. I seem to have given this talk many times over the last 6 months or so. Some people have heard it several times, so I hope you brought something to read, or you can always check your email or something. Take a brief nap, okay? Also, I'm slightly jet lagged, so if I'm not don't seem to be making any sense, that is probably because I'm not making any sense, and you should tell me so. Okay, so this talk is roughly speaking about arithmetic aspects of mirror symmetry, or maybe say it's inspired by arithmetic aspects of mirror symmetry. So let me start by giving you two sort of examples. So take a smooth hypersurface in P1 cross P3 of degree 1, 2. So this has odd cohomology, which will be important. In fact, it's the blow up of P3 along an elliptic curve, which is an intersection of two quadrics. And the first Chern class is 1, 2. So when you look at mirror symmetry for this, the traditional way is to write down a mirror superpotential, which is not unique. Right? So it's a Laurent polynomial. Okay. Which I conveniently looked up this morning in Alessio-Corti's database. This is not canonical, but what is canonical is the quantum period. Okay, so in terms of the original symplectic geometry of the original thing, this is given by, it's a function of some formal parameter. And it's so they're Gromov-Witten, genus 0 Gromov-Witten invariants with gravitational descendants, suitable power of the gravitational descendant, so that this one here is actually a number, and assembled into a formal power series. Now, in terms of these superpotentials, the way that these are written is so you take 1 over 1 minus h bar times this superpotential, and then the volume form here. And you integrate it over the coordinate torus, or to make it completely explicit, let's say it's you take w to the d, and you take the constant term, and h bar to the d. Okay? Sorry, w is the superpotential. Okay? Yeah, here I should divide by 2 pi I cubed or something. Yeah, there you go. So, so in this example here, for instance, d2 factorial, d1 plus 2d2 factorial, and so on, and there's this power here, h bar d1 plus 2d2. Okay? So these things here have a meaning in terms of the, so while the superpotential is not canonical, its period is canonical, and indeed can be identified with this generating function for 1 point Gromov-Witten invariance. Okay? So the let me give you one more example of the same computation. Okay. This is a much simpler example. Okay, x in P5, the intersection of two quadrics. Okay. So this one here has second cohomology Z, and the first Journ class is twice times the generator, and it again has odd cohomology. So in this case here, because the first Journ class is 2, so if you look this up in Ludmill's most recent paper, Z4, thank you very much. Z1 plus 1 squared. No. Hold on. Yes, you're right. Sorry, yes, you're right. Okay. Z2 plus 1 squared over Z1, Z2, Z3 plus Z3. And yeah. And it's so the superpotential So this has only even degree terms because the first Journ class is even. Okay, so these will not return for quite a while, and I hope I will get back to them at the end. Okay, so now let me say a few general things. Okay, so these both things, these are closed, monotone symplectic manifolds. In fact, there are Fano varieties, but I use the anti-canonical class as my symplectic class. Okay, and so then I have I can define the Fukaya category. Well, the Fukaya category is a family of categories had parameters, but in this case here, I can specialize the parameters and get a Fukaya category defined just over the integers. Okay, let's call this A. Okay, and then I want to take the Hochschild cochain complex. Okay, so this carries the structure, in general algebraic reasons, this carries the structure of an E2 algebra, or algebra over the little disk operad. Okay. So there are various explicit algebraic models for what this structure looks like. So suppose, for simplicity, that A is a differential graded category, which is of course not true, it's an A infinity category, but I could replace it by a quasi-isomorphic DG category. So then the E2 structure is generated by brace operations, okay, which are very natural operations on Hochschild cochains. Well, there's of course the differential, then there is a sort of product that uses the product structure on A, and then there are operations like this, where you insert a bunch of Hochschild cochains into another one. Okay, so what I'm interested in is our solutions of the Maurer-Catan equation. Okay, so where I take This is all Z2 graded an odd degree thing, and it satisfies this equation here. That is the Maurer-Cartan equation. And two Maurer-Cartan elements are isomorphic or equivalent. If so, I have two Maurer-Cartan elements, say gamma and gamma tilde, if they can be written as like this. The signs might be incorrect here, okay? For H in C. No. That's correct. Okay, even, C even, okay? So far, to be honest, I haven't actually used the braces at all. All I've used is, this operation here, which makes this, the Hochschul complex into a differential graded algebra. So the equivalence classes let's call this MC for Maurer-Cartan, carry a group structure. Okay, so where I say okay, it looks like this. Actually, so this is if you have, there's also the operation, d equals 0, phi, the empty bracket, by definition that's just phi itself. So that's actually gamma 1 plus gamma 2 plus these sort of nonlinear terms. Okay. Now here, there's an obvious convergence issue here in the infinite sum. So in fact, the convergence issue has been there throughout. So I have to introduce some coefficient ring that makes things actually converge. Okay, and so here n, say it's a some sort of pro-nilpotent ring, right? So it's a non-unital commutative ring. So this means that okay, so e.g. n is q z double bracket q, so formal power series with vanishing constant term. And now everything that I wrote down makes sense. Okay, so for each of these coefficient rings, I get a group structure, a set, the set of Maurer-Cartan elements, which is actually a group. Okay. So even though this is maybe not literally true in general, you can think of this as this MC of script C as being a formal group, and of these as being the sort of n-valued points of that formal group. N could also be DG and so on, but for the moment, Okay, so there is actually a simpler, you can say, well, why do the Maurer-Cartan elements in the Hochschul complex form a group? Well, this is actually not surprising, as Maxime said it. So if gamma is Maurer-Cartan, so that means that if you do this one here, so the identity plus gamma is a curved A infinity homomorphism of A tensor hat. Okay, so you have the identity here, so it reduces, it's a deformation of the identity endomorphism of the category. If you do work mod n, then you just get the identity back, and so it's a family of curved in general A infinity homomorphisms, and of course so endomorphisms. Okay, so it goes from itself. Okay. And of course, you can compose A infinity homomorphisms, so therefore they form a group. Okay.
Is another way to say this that the problem of deforming the diagonal diagonal shape is loops of the problem of deforming the category?
Yeah, fair enough. Yes. Okay. Yes. Okay. So if you're worried about the sort of asymmetric looking here, where it seems to be linear in gamma 1 and non-linear in gamma 2, that's sort of an artifact of the particular presentation in terms of the braces operations. Okay, from a geometric perspective of E2 algebras, this is it's not a commutative operation, but what I mean is the two things appear in a sort of symmetric way. Okay. Right. So okay. So there is one part of this formal group structure that you can get a handle on in a slightly simpler way, which will not surprise people who are used to deformation theory and characteristic P. So the special case means special case of coefficients. Okay, so you take n to be equal to, well, first of all, I've reduced coefficients to fp. Okay. Well, I guess I called it q here in the example. Okay. I don't really have a. Okay. Vanishing, so fp formal power series, and then I divide by p plus 1. Okay. So I have for this particular n. Okay. So. And I want to look at, this has a group structure, so in particular, I can look at the pth power map with respect to this product. So this is associative product. So pth power, p times gamma product with itself. And that has a fairly simple interpretation, namely, let's truncate here and do q fp q mod q squared. Okay. So this is a coefficient ring now where the square of any two elements is 0. So the Maurer-Cartan equation, which I unfortunately no longer have, just becomes the equation to be a cocycle, and the equivalence relation, so these are all zeros, so there's no products, just becomes the relation of being homologous. So this is just the odd cohomology of C with fp coefficients. And similarly, if I have this one here, q fp q over q squared. I can map this here by taking q and substituting q to the p. And this one here is the same thing. Okay. And so there's a commutative diagram here. So basically this means that, here you have a Maurer-Cartan element, and it starts with a term of order q. But when you take the pth power, the order q term just gets multiplied by p because of this one here. But also maybe P is a prime.
It's the degree of odd. It goes from odd to.
This goes from odd to odd. Yes. Okay. So this is. Yeah, it also goes from odd to odd. Yes. Yes. So the. So but not only the order q term disappears, but also the order q squared and so on. And the first non-trivial term is something that has a q to the p. Okay. And this one here is an operation here on the odd. It's on the odd cohomology, not generally speaking an additive operation, and this is called. So on the cohomology of an E2 algebra with coefficients mod p, there are only two operations that are sort of universal. These were analyzed by Cohen, and this is one of them. Okay. So it's a sort of Cohen operation. So you can sort of hope to get a handle on this simply because it's defined on cohomology, so you no longer have to look at this nonlinear sort of operation. Okay, so this is all, I would do it. This is something that you can do with a Hochschild cohomology of an arbitrary associative DGA. Really, I wanted to do it with the Hochschild cohomology of the Fukaya category, in which case it should have a more geometric meaning. Right? So, which I will explain now. Are there any questions at this point? So, okay. So now we return to geometry a little bit. Okay, so returning to geometry. Okay, so I wanted to look at the Hochschild complex of the Fukaya category of X, but there is a map just from, okay, the closed open map. And this map here should be a quasi-isomorphism. Well, in many cases we can prove that it is, and if it isn't, and you ask somebody, they would say that, you know, the answer to that should be that we should change the definition of the Fukaya category until that becomes true, more or less. But so we'll just replace it by, so let's work with instead. Okay, so this carries the structure of an E2 algebra. Okay, essentially through Gromov-Witten invariance, and this is supposed to be a morphism of, this is a morphism of E2 algebras. So we get a formal group MC of X, which are Maurer-Cartan elements, just an ordinary core, with respect to this. But what I mean by this is that if you take a coefficient ring n, then you get a group structure with n coefficients. Okay? Okay, and so what is the counterpart of this one here? So this is okay.
I got a bit distracted. Which E2 algebra structure are you putting on chains?
Well, from Gromov-Witten invariance, right? In fact, so let me say this will become clearer in just a second, okay? So in fact, the E2 structure is part of the action of chains so this is what's called the cohomological field theory structure. Okay? Yes?
Cohomological field theory is like after you take cohomology usually.
Okay, fair enough. Okay, but so
This is actually a thing which exists. This thing acts as chain level.
so this should then be called, you know, a topological conformal field theory, I think. That's what Seidel
That's
calls
the thing which exists. You give an action at chain level.
Yes, we have an action on the chain level. Yes, of chains on the Lie-Mumford space. This acts on the cochains on X. So inside this one here, this is the Lie-Mumford space. So inside this sits the configuration space of n points on the plane. We put one point at infinity. Well, it maps to it. So through this map here, it inherits the structure of an E2 algebra, but it's an E2 algebra which is in a sense degenerate because it extends to this larger space. Now this degeneracy has a couple of consequences. Okay, so corollary. Yeah, I use the fact that it's monotone so that I can do everything over the integers. Yeah. So this is everything works over the integers. So the corollary of that is that the group structure product, this dot product here on I mean, I'll put in the coefficient ring to be honest, is commutative. Okay, something which is not true in general homological algebra, but is a feature of this situation here and is somehow related to the Calabi-Yaunes of the category. Okay. The other corollary is, okay, so now I will do the thing which everybody hates, which is a stealth edit of this one here. Okay. So when I do this, so usually, of course, you have this kind of diagram and you have some kind of Cohen operation, but so let's see. So now I'm replacing this one here by cochains on X, cochains on X. Okay. And here, well, there's cochains on X, but really, this is just the cohomology of X. This is the cohomology of X. This is cochains on X. But now so this is, of course, still true. It's just an instance of the, if you want, well, I've replaced, if this was a quasi-isomorphism, it would be an instance of the previous one in this, but it's a general property for E2 algebras. So, but now I want to call this something else. Okay. So, which is something that you can only do in this case here. Of an algebra of the Riemann-Manifold operates, okay, where star is, okay, there is some horrible constant, p minus 1 over 2 factorial inverse times the t to the p minus 1 over 2 coefficient of the quantum Steenrod p-th power operation. Okay, so what is the Steenrod p-th power operation? Okay,
Can I ask you my
yes.
question again? What happens when p equals 2?
Yes, okay, so in this case here, this is relevant. So this is not a problem, right? This is just 1, okay? So in the case p equals 2, as you... 2 minus 1 over 2. Oh, sorry, it's just 1. Let's define it to be 1, excuse me, for p equals 2. So for p equals 2 equals to 1. Okay, and this one here, as you will see in the p equals 2 case, so this here, I have not explained what this is. This is an element of the covariant cohomology of a point. So in the case p equals 2, there is something which is a square root of p, a square root of t. So that actually makes sense. Excuse me, so that one here, yeah. So, yeah. Okay, so now I will, so what are quantum Steenrod operations? These were defined by Fukaya first, at least for p equals to 2. You know, for this case here of monotone symplectic manifolds, and they also exist, you know, there used to be these things like the weakly monotone symplectic manifolds and so on, where people used to do some kind of subclass. They're not, as far as I know, defined for general symplectic manifolds, and they've sort of been left behind by history, which means is, you know, the definition is sort of ad hoc in terms of counting. By now, you know, we're used to saying you need a modular space with nice property and its virtual fundamental class. And the Steenrod operations somehow do not have this that I know of, which is very disturbing. Okay, but they, you know, they do exist. Okay, so let me show you how they exist. Define them in terms of this cohomological field theory, or whatever you want to call its structure. Okay, so the quantum Steenrod. Okay, okay, so. Okay. So I start with the cohomology of my manifold with coefficients in Fp, and then I take the sort of p-fold cup product. Okay, so p-fold product. Okay, there's a topological operation. It has a slight refinement here, which is that you can make it land in the ZP equivalent cohomology. Okay, intuitively, this is kind of obvious. If you took the Poincare dual here, would be a chain. Then you take the chain cross itself. That's naturally Z mod P invariant. Okay. So now I have the, well, I'm just still. You have this action of the cohomological field theory, and so you end up in So I want to look at P genus zero curve with P plus 1 points, so P inputs and 1 output, and I'm going to pull back things by the evaluation at at the P inputs. And so you get a map that goes to here and is still Z mod P equivariant. Okay? Now the Z mod P action, here is the action which cyclically permutes the first P points and leaves the other one, P points and leaves the other one alone. And it also acts trivially on X. Okay? So really, what we have here is you have the ZP equivalent cohomology of M0 P plus 1 with coefficients of Fp, tensor the ordinary cohomology of X with coefficients in Fp, and you take the whole thing in degree P plus Pi. Okay? So now the equivariant cohomology of M bar 0 P plus 1 with coefficients in Fp is unfortunately unknown to me. Okay? But you could try to approximate by using, let's say, localization. And so you look at the fixed points of the Z mod P action. And the fixed points are really easy to describe. Okay? So okay. So here are the fixed points where you arrange your P points symmetrically along a circle here, and then the last point you put here, and then you can see that there is this rotation here which cyclically permutes these points. Okay? And so this is a fixed point here, and yeah.
Why degree is the same Pi because it depends on degree of curves?
Oh yes, I'm terrible. So here it's it's mod 2. Okay, so now here it's mod 2. Excuse me. Okay. So as soon as I apply the cohomological field theory action, all degrees are sort of mod 2. And I apologize. Okay. But so what I wanted to say is, so you restrict to the fixed points, which is this is a fixed point here. And so this gives you so a class ZP of a point, tensor the cohomology of X, again with coefficients, okay, Pi. And so this one here is the quantum Steenrod Pth power. Okay, there are a number of nice aspects to this. In this case here, so due to the extension of the structure from the E2 structure, which means from configuration space to this, you can identify this particular Cohen operation with this particular quantum Steenrod operation. And it's nice, for instance, while these operations here are not generally speaking additive, this operation here is actually additive. Okay? You might say, wait. The p-fold product is not actually an additive operation, which is true. Okay? But it's stably additive, which means after multiplying with some element of the coefficient ring, which I will write down now. And okay, so here, so 1 second. So my notation here, h star zp of a point with coefficients in fp is fpt plus theta fpt, where t has degree 2, theta has degree 1, and on popular demand for p equals 2, theta is written as t to the 1/2. Okay? So this explains this one here, the t to the power p minus 1 over 2 coefficient. So here, this is an operation on cohomology, which depends on these auxiliary parameters, t and theta. And you extract the coefficient t to the p minus 1 over 2, which in the case p equals 2 is actually the theta coefficient. Okay? So, and so the general homological algebra theory for chain complexes is that this kind of product become additive, so linear after multiplication with t. However, here there is no t torsion, so it must be additive altogether. Okay?
Is there a non-commutative
Are you working with like cohomology of the actual space? If you were still working at the level of Morita-Cost scheme, definition theory of the diagonal bimodule, is included in this kind of...
Oh, whether there is a simplification of the product, of the Morita-Cost product?
Yeah.
That is a good question. I don't know. So the simplification of the Morita-Cost product means, in terms of E2 algebras, you're thinking of an algebra that has operations given by some kind of configuration spaces, or maybe Fulton-McPherson spaces, and there's certain cycles in these spaces that give you these products. And so if you wanted to simplify it, you would then map these spaces to Deligne-Mumford spaces, take your cycle, and try to move it into some better position. Okay? Which I have not tried. I've only done it for this special case here. It's a good point. Okay, so, so let's summarize where we are. So I have a monotone symplectic manifold, a Fano variety, and I can look at this, this MC star, which is this set of quantum Morita-Cost elements, and this carries a group structure, which is of course hard to understand. It's given by chain level Gromov-Witten theory. I think that's the correct way to say it. But if we specialize to this particular coefficient system and we look at these p power maps, which is what people in formal groups often do, then we can realize this here in terms of quantum Steenrod operations. Okay? Now you might say, well, that does not actually help me at all, because the quantum Steenrod operations are as mysterious to me as anything else, which is fundamentally true. But in some cases, you can sort of... so the question of what the quantum Steenrod operations actually are in general, I think is an interesting question. Okay, so So what's actually happening is that the quantum Steenrod operations take place at a particular point in Deligne-Mumford space. So they count maps. Okay, so you take this particular surface with these points here, say z0 equal to infinity, say this is c bar, and you have these points here. Zk is, let's say, e to the 2 pi k over p, k equals 1 to p. Okay, this is this particular curve. And you're mapping this one here to x and the input points to x to the p. Okay, so zp equivariantly. Okay, so in some sense we use pullbacks and push forwards, but using this ZP equivalent cohomology. Okay, so the space of such maps carries a ZP's action, so it's a compactification as a stable map. It carries a ZP action just by rotation, right? I mean, you permute this curve here as this ZP symmetry, but of course the actual, sorry, maybe I should say, okay, there's this map here to X, so map U, okay? So under this symmetry, the map is not necessarily preserved, right? So you take this particular curve with these marked points, and you take stable maps to X, and the moduli space carries a Z mod P action just by acting on the curve. Okay. Sorry, I'm just wondering how unclear I actually am. So okay, and so since what you're actually doing is, you're computing sort of intersection numbers on that space, if you like, you could think, well, I'm going to apply Z mod P localization, right, to compute these. So the fixed points of the ZP action, okay, so they're ones which are actually the most interesting ones. So they're p-fold branched covers of of these maps here, okay? So you put one branch, you take this is a rational curve, and you take a p-fold branch cover with 2 branch points. You put one branch point here and the other branch point there, and then the pre-image of this will be p points, which will be this one here, okay? But there are also others which appear, in the compactification. So you could do the following thing. Okay, I have, sorry. But this is a constant map, okay? And then you have some other map with only 2 map points, okay? So this is not actually a branch cover. Its homology class does not have to be p-fold, p times something. And the same thing is you could have, so this component here, this carries all the marked points, but this has a constant map, and you have another thing, and maybe, okay? And you can also combine these two, okay? So these are all fixed points. Okay, so so this is potentially interesting because, we love branch cover contributions is something that, at least on the symplectic side of Gromov-Witten theory, people have always worried about. But it's a little tricky to think about because of the fact that we're missing a proper, virtual fundamental cycle framework, right? I mean, this thing here, so let's assume that this does not happen.
Can you explain what?
Excuse me?
What virtual cycle?
Well, in principle, I would like to have this space here, right? The space of maps here, to have a virtual, a ZP equivariant virtual fundamental chain with FP coefficients, right? But this is an orbifold with, even in the most optimistic cases, this is an orbifold at these points here with isotropy that is a multiple of P. So, it's very, apart from not being actually smooth at these points here, but, even if you think virtually, there are certain issues here, okay? Well, not unsurmountable issues, but, But so this is the easy case. So assume this does not happen. How can this not happen? So we consider, so suppose you have a class here. Maybe say sum over some Cj represented by holomorphic spheres, okay, by a rational map, okay. So if I assume that you can't write it like this, then, well, this assumes it's not a p-fold branch cover, and then you add other stuff, then it cannot be even a p-fold branch cover with a bunch of things attached to it. And then these ones here, these ones here, we can understand these contributions here by localization. Namely, up to maybe minor technical issues. So here, look at these maps here, okay? So here you have a constant map with a Z mod P action that rotates the inputs. Because it's a constant map, what happens here is essentially what happens in the definition of topological classical Steenrod P's power. So this map here takes these P inputs and produces an output which is actually this classical Steenrod P's power, okay? And this one here looks like an ordinary two-pointed Gromov-Witten invariant. You have to be a little bit careful. This is a stratum in the moduli space, and when you apply localization, you need to know its equivariant Euler class. And so the Euler class of the normal bundle. So the normal bundle involves smoothing out this node here. And when you do smoothing out the node, you take the tensor product of the tangent lines at this point. But this tangent line here carries a non-trivial Z mod P action. So in this case, actually, you will see the tangent line at the other end arising, which means that you get gravitational descendants. But you can write down a formula for this, for these contributions in terms of ordinary Gromov-Witten theory with gravitational descendants. Okay, which, yes?
So does that sound like what you explained is that you weren't really using the CFT structure? This is just some structure you saw. These pictures are CFT pictures, right? You've gone to the boundary.
Okay. Yes, these pictures are CFT pictures. That's absolutely correct.
What you explained sounded like you don't, maybe to interpret it, you're using these CFT pictures. The actual structure depends on the
Sorry. All right. Yeah, so sorry, I should say. So I'm still trying to compute this Pth power map, right? And this Pth power map is something that comes from the E2 algebra structure, so it's completely independent, you know. But to give a simple formula for this, I use this kind of CFT structure, right? So that enables me to give a much simpler expression, because instead of using a cycle of certain dimension, I actually just use a point cycle, okay? And I can reduce it, you know, at least in this case here, which I don't know how to handle yet. I can reduce it to ordinary Gromov-Witten invariance with descendants. Okay, and now the question is, you know, what actually comes out of this in the end. Okay, so now I go back to the examples from the beginning. Okay, because things happen that I do not understand why they happen. Okay, so. Okay. So example B, which is the slightly simpler example, okay? So X is in P5 is an intersection of quadrics. Okay? So then what am I looking here? So what I'm looking here, remember I'm looking at P minus 1 over 2 factorial inverse times the T P minus 1 over 2 component of quantum Steenrod P, which is an endomorphism of the odd degree cohomology. Okay? And so what this turns out to be is just minus 1 to the P minus 1 over 2 times the identity on the odd cohomology here. Okay? So this is an expression for the leading coefficients of the Pth power map of a certain formal group. So where have we seen this before? Okay, so this is, and in fact, there is a well-known group, just algebraic group, which shows this. Okay, so the non-split rank 1 torus, okay, which is this group here. Okay. Okay, which is where I is just a formal symbol whose square is minus 1. Or if you don't like the formal symbol, you can just write them as rotation matrices. Okay? So this is an algebraic group. You can take its coefficients of any field. And so if you take it, you know, mod P, so it's... So only the two leading order terms survives. Okay, P minus 1 over 2, y to the P. Yeah, this would maybe a moment where you don't want P equals to 2. Okay, so. Okay. And so, so if you look at the formal expansion, near the identity element, so then y is a coordinate. Okay? And what I've shown to you is that the Pth power map in this formal coordinate takes exactly this one here. It's the identity times, you know, well, it's p times minus 1 to the p minus 1 over 2. Okay? Which should mean, I mean, that's not a proof, should mean that the Fukaya category under consideration, if you consider its automorphism group, and if you consider at least the formal expansion near the identity, it looks like the product of 4 copies. This is fp to the 4 of 4 copies of this non-split rank 1 torus. Okay. So the first question that I don't understand is I should see this somehow from the known superpotential, because actually when you compute these things, sorry, I have not written down how you get these, you actually eventually extract them from certain coefficients of the quantum period. Okay? So the quantum period was quite complicated, but mod p is actually rather simple. And so you extract this one here from certain coefficients. So this should have a meaning in terms of the geometry of the superpotential, which I don't know. And I'm especially interested, if you can say something, about why we get the non-split rank 1 torus and not just the multiplicative group. Okay? So the other example, the example A, so this was x in P1 cross P3 of degree 1, 2 is a lot more interesting arithmetically, unsurprisingly, okay, which is, okay, so in this case here it turns out that p minus 1 over 2 factorial inverse times the same thing here, I'm not going to write it down, that this is, so you extract this from the quantum period, and it looks like this, 1 over d1 factorial squared, d2 factorial to the power 4, which is, you know, this is in fp, right? This all makes sense because there's no 1 over p's here. Okay, let's call this one here a sub p. Okay, so these come out of the quantum period, but they also have a different interpretation. Okay, so AP. So now I'm going to extract them from a different Laurent polynomial, which so this is the constant coefficient. Yeah, so this looks like a period, but it's a different function here. x0, x1 plus x2 squared plus x3 squared, x2, x3 plus x0 squared plus x1 squared over x0, x1, x2, x3 to the p minus 1. Okay? So this is sort of just combinatorics in terms of this. And this one here, this is, so the number theorists are very familiar with this kind of thing. So they would say that this one here, for elementary reasons having to do with little Fermat, is p plus 1 minus the number of fp points on this curve here, on EFP, where E is this, you know, you have two quadratic polynomials here. So they define a genus 1 curve in P3. Okay? In spite of the fact that I've called it E, it's not an elliptic curve over Q, but it is an elliptic curve over FP. And this counts the number of FP points on it, or, you know, if you wanted, it counts the number of FP points on its Jacobian, or and indeed on any isogenous elliptic curve. So it is a theorem in number theory that these formula here, p plus 1 minus the number of FP points, they also describe the pth power map associated to that elliptic curve. Maybe I can find space to write it down somewhere here. So, okay, so.
These are just the two factors in the.
Yes, these are the two factors there. And this is always the diagonal term. And this is kind of a stupid trick involving little Fermat. Well, that's a good question. So, okay, just let me write down, sorry. So second also, so the, so, one second. Okay, so the formal group associated to EFP has pth power map. So if you have some formal variable, I don't know what, t, maybe t is not a good idea. Okay, q goes to z, z goes to z to the p times a sub p. Okay, plus dot. Okay, so yeah, so the problem is that, so we have okay, and then what we did originally was we used the constant term of w to the d, right? So those are the, this is the quantum period. Okay. Okay. And so here we have E, we have a genus 1 curve. And so we have, point counting. Okay. And so the constant term. Okay, so if I say this, if I call this f equals g equals 0, constant term of fg over the diagonal monomial. Okay. And I am honestly completely perplexed. So I didn't do computation in this example, but I did it in the other example. And I tried out a couple. So the superpotential is not unique. The mutations you can apply to, but I can never actually get to see this thing here in the critical locus. You have to remember that the superpotential describes the mirror up to a gap of complex codimension 2, right? And it is perfectly possible for a whole elliptic curve to fall into that gap, which no mutation of the superpotential can ever describe. Okay? However, if you somehow compactify the superpotential, you should be able to see it. So I am hoping somebody would help me. The thing which I'm much more worried about, but this, I'm optimistic, right? I'm slightly less optimistic. I would like to see the simpler example first, and why the heck. So when you compactify the superpotential, you should see a piece of the critical locus whose automorphism group is the non-split rank 1 torus. This has to be done over the integers in order for this to be effective. In principle, you can, inside this isogeny class of elliptic curves, there are over Q, there are 5 or something different J invariants that you can look at. So in principle, there are things you could check over the complex numbers. So this is this one here. There I'm hoping that somebody will just help me out of my misery. Here I'm slightly more confused. So so here the constant terms, this quantum period, that just arises from the most basic things in mirror symmetry, like Giventel's solution of the quantum differential equation and the quantum D module. Okay, and I get to extract the constant terms of power of this potential. Here, I am extracting the constant terms because it's some way of counting the FP points mod P. So I'm assuming that somewhere in arithmetic geometry there is a connection, a motivic connection between these period integrals that I'm doing here and the point P counting, and that I should be able to understand this. I have absolutely no idea. Thank you very much.
coming from the same things like you have counting. There was isomorphism between the RAM homology and without the RAM differential multiplication by the F, mod P by Palagotsky-Ovus. And you get certain matrices, for example, you get like periods of exponential motives mod P, and they can contain usual periods, usual matrices. Yes, it's really not a big deal. What on the right hand side you have isomorphism between the RAM homology and Hodge homology, homology of variety with forms without differential, and mod P story gives you isomorphism, and matrix coefficients of such things gives you counting mod P. Okay, and here it's
Okay,
exponential period.
I will need this slowed down slightly.
Okay,
yes.
yeah.
Other question? So you mentioned that the CFT told you that it was a Abelian group.
Yes.
Is that, can you say something general? Like, one might have thought that the moduli space was already a group. If you're getting an Abelian group, a space loop space, then maybe moduli space was already a group or something like that. I don't know. Which is what, is there something you say about the moduli CFTs that tells you that the governing object is going to be an Abelian group?
Isn't it from the formality that comes from the BV structure? You never mentioned the circle action.
Yeah, so it's part of the triviality of this. So, I mean, it's the same reason why, strangely enough, on a Calabi-Yau, well, so the simplest thing would be, why is the Lie bracket 0, right? So on a Calabi-Yau, the Lie bracket between holomorphic vector fields is 0, and that's easy to see in terms of writing it in terms of the BV structure. Okay. Exactly what I need for the higher order things, I mean, it comes from trivializing actually half of the circle action, because you take the picture which gives the product and you just rotate it by 180 degrees. But that is more or less what. So you might be able to get away with slightly less than the triviality of the circle action, but I'm not entirely sure. Triviality of the circle action is the same thing as extension over the Lie-Mumford space, right? But exactly what you need, I'm not sure.
So I got confused. When was equation satisfied? The sum of squares. That's definitely a critical point of this potential. It's an elliptic curve.
Yes.
It really sits in a critical locus. Yeah.
Really, it does.
Yeah, no, just look, equations are the same. Yeah, you take constant terms, so you just repeat the same.
But that's on the other side. I think.
Sorry. No. What are you saying here? Sorry.
I get elliptic curve given by two equations. Yeah?
Yes.
And then I just remove 1 meter left. Yeah. You see just product of these two equations.
Yes.
So
You say the critical points of this.
Yes. Yeah.
Yes, but that's not the original superpotential, right?
Ah,
So maybe there's a birational transformation between this and the original superpotential that I haven't found.
I just checked the calculation. You get the same residues. Yeah. That's it.
Yeah.
So, but this is the elliptic curve on the original one, right?
Well, I don't know. I just reverse constructed this curve here from this expression here. Okay. So I have no particular motivation for this. But yes, presumably you should write this as a critical locus of something, and then you should make a birational transformation between that and the original superpotential.
But what's this reverse construction? I mean, how does one go from that series to this to the following? How do you know that AP? How do you work out that AP is the constant coefficient of it?
Are you asking about the relation between this and this?
No, rather between the
This and that.
Yeah.
No, that's some kind of stupid combinatorics. I mean, you take the p minus first power of this, and you count, how many different times can I do this and that. And there will be some p minus 1 factorial up this, but the p minus 1 factorial is minus 1. So there's p minus 1 factorial square or something up there. This is some kind of silly combinatorics. But
You told me if I know the bottom, I can reconstruct the top.
no, I started from, well, either way. I mean, I made a guess at where this could come from, in terms of this.
All right. So since we got both ratio and 215, so I